Here we have another problem that we're going to look at. Trucks' brakes can fail if they get too hot. For anyone that lives near mountains, drives through canyons, you've probably seen the runaway ramps to help trucks stop if their brakes fail. So here, I'll draw my picture over to this side. So we're supposing this gravel ramp slopes upward at 6 degrees. The coefficient of rolling friction is 0.4. We want to use work and energy to find the length of the ramp. So however long the ramp is, that's going to stop our truck that has a mass of 15,000 kilograms. And we're assuming the truck is traveling at 35 meters per second as it enters the ramp. So conservation of energy, our basic equation that we have in the test notes, looks like this. So we're going to relate the energy the truck has at this exact moment in time to the energy at the time at which the truck has finally stopped. That's what we're doing when we do work with kinetic energy, relating energy at 2 moments in time. Now, as far as potential energy is concerned, the only type of potential energy we have in this problem is gravitational. There's no spring, so we don't need to account for that. There's friction. We're going to account for friction in the delta E thermal term. So that will be the friction force times the distance it acts over. Kinetic energy we know is 1/2 mv squared, and the truck has kinetic energy while it is moving. So at this initial moment in time, if we define the bottom of this ramp as y equals 0, which we can define that wherever we would like, since g is constant, then initially the truck has no gravitational potential energy, but it certainly has kinetic energy because it's moving. At the very end, at this final moment in time, there is gravitational potential energy because the truck ends up at a height, y final, above where it started. And there's no kinetic energy because the truck has stopped. So if we come over to our conservation of energy equation, we're saying we have no potential energy initially. We do have kinetic energy. Work external, if you remember, that's work done by forces that are not our friction, that are not our gravity and not a spring. We don't have any other forces that are responsible for changing the energy of the truck. The only other force that we would have on the truck would be the normal force, but the normal force is perpendicular to the motion, therefore it does not do any work. Finally, we will have that gravitational potential energy. The truck is not moving, so there will not be kinetic energy, but there will be some thermal energy that has been generated because of the rolling of the tires through the gravel. So we're going to plug in these individual equations we have for this initial kinetic energy equaling our final gravitational potential energy plus the thermal energy generated. We know the mass of the truck. Let's see, we know that initial speed. So we know mass, we know initial speed, we know mg. We do not know y final. It's okay. D is going to be the distance along the track, along the ramp. So I labeled it L originally. We can call that D or put L in our equation. The force of friction comes from knowing that friction is mu times N. If we draw our little free body diagram, we know the normal force is going to balance out with this mg cosine theta part of gravity. And so we can say the force of friction is that coefficient times that normal force. We have the information for friction, but we don't know D. And D is ultimately what we're trying to calculate for. Let me go ahead and plug in the friction force. It's rolling in this case. So the normal force and then the distance it acts over. And just a total side note, this D is really easy to forget. I see that commonly done. Like, that's a common mistake I see on exams. So just make sure you have the force and the distance. Now, if we go back, again, we have these two unknowns, y final and D. But if we think about this ramp, if I just draw it to the side, a little smaller just because I'm lacking in room, D here represents the ramp length itself. Y final represents just that Y side, that vertical side of the ramp. We know the angle. We don't know either side, but we can totally relate Y final to D. So 6 degrees, we know the opposite side and the hypotenuse, so we can say that the sine of 6 degrees is that opposite side over the hypotenuse. So Y final is D sine of 6 degrees. That doesn't give us the value, but if we plug in that relationship here, oh, not Y, sorry, mg, and so in place of y, I'm putting d sine of our angle, 6 degrees. Finishing out, I can go ahead and put my 6 degrees right there. By doing this, we now have d as our only unknown, which is nice. It also turns out that there is an m mass in every term, so we can actually cancel that out. We don't need to know the mass of the truck. So if I rewrite this, I can factor out the d, and that will leave me with g sine of 6 plus mu g cosine of 6. We now have everything except for d. D can be calculated by v squared over 2. Oh, I can factor out the g. Let's go ahead and do that for minimizing plugging in our numbers. So the 2 comes from the 1/2. I'm factoring out the g because I'm dividing this these terms in parentheses over to the other side. That leaves me with sine of 6 plus mu cosine 6. So plugging our numbers in, we were told to assume the truck enters the ramp at 35 meters per second, which we need to square. And then mu, they told us, was 0.4. Just plugging it into my calculator now. 6. I'm getting 124. Let's see, we have 2 sig figs, so approximately 120 meters per second. Or sorry, meters, not meters per second. It can be helpful to follow the units through. In the numerator, we have meters per second for the speed, but then we're squaring that. So in the numerator, we have meters squared over second squared. And then in the denominator, the only units we have are associated with g. So meters per second squared is what leaves us with those meters. So again, watch for the common approach. Conservation of energy tends to be a favorite once we get a good feel for how to use it, because we're just looking, hey, the truck has this energy initially, has this energy finally, and setting up an equation that describes that relationship mathematically. So I'll do a couple more examples, and we'll finish up this chapter.